If you're new to this channel, you may consider subscribing and hit the bell icon so that you continue to receive the updates. Please share it with all others who might benefit. Let's get started. In this video, we're going to take up another classification case study, which is from the healthcare background. Essentially, this is about predicting the stage of cirrhosis. This data is slightly old, but this is a very valuable data because this is a real data and the observations here were collected over a span of 10 years. It's a real research that was conducted on various patients who underwent certain clinical trials. So we'll provide you a link to this dataset, and at this place itself, you will find a proper description relative to all the fields which are relevant and which we are going to use to predict the stage of cirrhosis. So we've modified the problem statement slightly. We are interested in predicting the stage 4 or the last stage of cirrhosis. That's how we are taking it up. Originally, this dataset talked about predicting 4 different stages of cirrhosis. That can be done, but the data is limited in terms of counts, about 400 plus rows. So we decided to make it a binary column. We'll be predicting whether the person is at the last stage or not. We have about 20 odd features which talk about different aspects related to the stage at which the patient participated in the study, the age, gender, and other pieces of information through the clinical trials. Let's get started. So we are at the Google Collaboratory, and I've already pointed to the data source, which is known as the cirrhosis dataset. And let's start by just calling the basic libraries, NumPy and Pandas. Then we read the data using Pandas read_CSV method. And let's check first few observations. So this is how the dataset looks like. We have an ID column, which essentially is a patient ID. Then we have the number of days, status, so on and so forth, and many variables. Like I said, it could be very interesting for a person who actually has a healthcare background, because you would understand what all these terms mean. Let's check the shape of the data frame, and we have 418 rows and 20 features. Let's check the data types quickly. So we seem to have a mix of numbers and categorical features, and we'll work on these separately. Let's quickly look at the names of all these features. So this is how the names of the features are. And just to have a look at the categorical features, because we know that for modeling, at some stage, we'll have to convert the categorical features to proper encodings. So what we're trying to do is we're trying to filter out all the categorical features by using the select_d types method. We are choosing all the object type variables, and we are going over each feature one at a time with the help of this for loop. Then we are printing the name of the feature and the unique categories within each feature. Then we are looking at the distribution through the value counts, and we are separating them with these equal to signs just for legibility. So you can see, for example, the column called drug only has 2 possibilities. There was a drug that was given in half the cases, and nearly half the cases we had a placebo. Placebo is not a real drug. It's kind of an impression the person is being given a drug, but it's more for psychological reasons. Then we have gender. It has 2 levels. Then we have ascites, which again has 2 levels. Then we have hepatomegaly, which again has 2 levels. We have spiders, again has 2 levels. Most of the features here, if you see, have 2 or 3 levels. So that's pretty much about the categorical variables. We can easily manage these variables through a dummy encoding or one-hot encoding when the time comes. Now let's look at the duplicates. Because we have an ID column, we have a unique identifier for each patient. It makes sense to check duplicates only with respect to that feature. Let's check this. If we have any duplicates using df.duplicated method, which is a pandas method, and it says 0. So we don't have any duplicate records in this data. It's a pre-validated data in that sense. Now, if there is no duplicate in the data, then we know that ID column is not going to be a predictor for anything. It would not determine the stage of cirrhosis. So we can drop the ID column safely, and that leads to loss of 1 column, which is fair because this is not going to predict the stage in any case. Then we have information about the feature called age, and age is given in number of days. So we are going to convert it to the years by dividing it by 365. Let me show you how the age variable appears. So the age variable looks like some value in thousands most of the times. We will convert it into years by dividing it by 365. That's what we are doing in our code. So we divide the age by 365 and round it up to 0 decimal places. Then we can look at the descriptive stats of the age feature alone. So you can see the minimum age of the person participating in the study was 26, and the maximum age of the patient was 78 years. And the median was 51. And mean was pretty close. So this data with respect to age seems to be pretty balanced in that sense. Mean and median are very close. Now we can check the unique categories present in the stage column. So this says that there are 4 categories and there is a NaN that's also available. Of course, for the target column, we don't tolerate missing values. So what we'd want to do is we'll simply want to drop the missing values, if any, for the target. We can do all the imputation for the independent features, but not for the target. So let's just drop this and then check the value counts in our case. So if you can see, there's a very limited data set. We have patients at different stages. Stage 1 are very few patients, then stage 2, then 3, then 4. That's how the counts are. Like I said, we will be primarily interested in predicting whether a patient is at stage 4 or not. So we'll have to make this column a binary. And how do we do that? So we simply apply a lambda function where we use this single line if else condition. If the value for a stage is not equal to 4, then we convert it to 0, which means it could be 1, 2, or 3. And if that's the case, and if it is equal to 4, then we convert it to 1. That's what it means. So we'll simply convert the stage column to a binary and check the distribution again. So we got about 144 cases at the last stage and about 268 cases at other stages, early stages. Let's check for the presence of missing values in our data. So we seem to have missing values. In fact, if you read the description of this data, it says that there are few patients who chose not to participate in the initial clinical trials and just gave consent for some basic tests. So we may not have information for all the patients available, but our model would need the information to be completed. So we'll see what we can do in terms of basic missing value treatment in this case. And we will refine it further over the subsequent case studies. So first of all, we are segregating the categorical and numerical columns. The ones which are object type are listed as categorical columns. The ones which contain floats or ints are listed as numerical columns. Then, by the nature of the variable, we are choosing a missing value treatment. This is the most basic missing value treatment, but this is where we get started with missing value treatment at least. So what we're doing is, for each column in the list of categorical columns, we are choosing the column and applying pandas fill-in method, where we are saying we want to put the mode as the replacement for the missing value. And mode 0, why? Because a given data can have a single mean and single median, but it can have multiple modes. So we are saying we want to take the first mode that we get, which is the most common value. Similarly, for the numerical columns, we are going through the list of numerical columns and we are saying we'll fill the missing values with the mean. We can choose mean or we can choose median. Let's just say we change it to median. I can modify this always. If you are worried about the presence of outliers in the data, then median is a safer bet. So I've just modified this to median now. And let's just run this. Now, once this is done, we can check for the presence of missing values again in the overall data frame. So we've just added an extra dot sum and says in the overall data frame, we don't have missing values any longer. At this stage, we separate the X and Y variables and split the data into two portions. So what we're doing is that we are calling the train test split from scikit-learn model selection. We are separating X and Y because that's how train test split accepts the input. And then we are saying we'll park about 80% of data for training and the remaining data for test. Now, if you see our data was slightly imbalanced, and if that's the case, what we can do is we can always add another parameter here, which is stratify is equal to Y, which is going to ensure that whatever distribution we do for train and test set has the same proportion of stage 4 cases versus the early stage cases. That's how we mention this here with respect to the Y variable. So let's just run this code here and see what happens. Now we've already done the split. We can check the shape of the data frame and we got 329 records in training and about 83 records in test. Y train wouldn't have anything different. It would have a single feature, same number of observations for train and test. We can check for the presence of duplicate rows in a way that's not needed anymore because we already checked it in the beginning through the ID column. And after that, there may be duplicates present as well. So for example, there could be two individuals of same age and they have similar parameters, but it's very less likely when you have clinical trial related information because you have values in to the precision of floating points. So it's less likely that all the health related parameters would be one and the same for two patients. And that's what in a way it confirms. So is the case with the test data. So this is a little redundant step. In a way, we know that would not be the case, but we're just checking. Now we're checking for the presence of outliers in the data. Let's just filter the numerical columns. First of all, we can get that list or we can just use select D types to get those. And then we are going over the list of numerical columns and we are creating the box plots. So we are saying for each index and column in the list of numerical columns, and we had 9 numerical columns in total, we want to create a box plot for each column. And this will be arranged in a 3x3 grid. This I+1 essentially is the index of the plot. So let's just run this here and you'll see the box plot. So we have 9 numerical features. If I scroll down, you can see these are the first 6 and these are the last 3 numerical features. So out of these 9 numerical features, we have about 7 features, at least we can say, where we have outliers present. Now in this particular exercise, we are going to focus on naive Bayes classifier, and naive Bayes has many variants. So when our data contains a mix of numerical and categorical features, we can use a Gaussian Naive Bayes. Gaussian Naive Bayes is not very sensitive to the presence of outliers because it in any case assumes that the data is normally distributed. Moreover, for healthcare data, if you see, when you have clinical reports, there could be extreme cases that we're trying to identify where the values may really be outliers. For example, the presence of cholesterol, the presence of copper. All these things could mean something from a stage perspective. It would not be fair to suppress and modify this data. So we'd not treat the outliers in this particular case. We'll let them be the way they are. We can check the same for the test data as well. And it's again, of course, it has 9 variables. And if we scroll down, it seems to have outliers for similar features. Some features here and there. For example, for the train, for this feature, we didn't have outliers. But here we seem to have outliers for this feature as well. And for this feature in the train, we had outliers here we don't have. But overall, like I said, we would not be interested in modifying this data because our motto is to predict the extreme stage or the last stage of cirrhosis. Now let's quickly glance through the distribution of the target column. In a way, we saw the numbers, but we can visualize it using a pie chart for the stage column doing the value counts. And if you see, this shows about 65% of the cases were the early stage cases, and about 35% of the cases were the last stage cases. So the data is somewhat imbalanced, but not that bad. It's not like a 95-5 kind of a ratio. 65-35 is fairly okay. We may also check for the correlations between the variables, but that's not going to be very useful for naive Bayes in particular. Why? Because it assumes that the features are independent. So we don't have to look at a pair plot for linear associations. If you just want to quickly glance through the correlations between the features, we can do this. So this is how the output comes. And we don't seem to have a very strong correlation anywhere in any case, right? So we don't have correlations like 90% or so. So this is fairly okay. The features are not that correlated and it would not even affect the specific model we are interested in. Now, the only piece that's left is that we have to encode the categorical columns appropriately. Fortunately, all the categorical variables had about 2 or 3 levels only, so it would be very simple to encode them using one-hot encoding. We are just selecting the categorical columns using select D types here and printing a list of those columns. And then we are saying, let's take this list and use get dummies from pandas to convert these categories into numerical equivalent using one-hot encoding. Please note, whenever we do one-hot encoding, we create as many columns for each features as the number of categorical levels are. And we, of course, drop one of the levels using this drop first is equal to true. That's something which we've explained at length in the encodings video. So you may refer to that if you need further understanding. Let me just run this. And we can now check the shape of the data frame. So if you remember earlier, we had relatively lesser number of features. Now we have more features. Why? Because we have done an encoding. So here's the shape of the data frame after applying encoding. Now we start with the standard Gaussian Naive Bayes model application. So we are calling the Gaussian Naive Bayes model from scikit-learn Naive Bayes, and we will be evaluating the model's performance through the classification report. So we are instantiating the Gaussian Naive Bayes model. We are doing a fit of the train encoded independent features and Y variable, and we are doing a predict on train. We are doing a predict on test. Finally, we are generating 2 classification reports separately for train and test, and we are looking at the output. So let me just generate that output for you, and then you can see. So let's understand what does it mean, right? So we are primarily interested in predicting ones here. 1 in our case represent the scenario of the last stage. That's a supercritical condition because this person won't have time. The recall of 51% here means that the patients who were at the last stage, out of 100 such patients, we are able to correctly identify only 51, which is not a good number to look at. And 71% precision here, 0.71 precision here means that whenever we said somebody is at the last stage, we were right 71 out of 100 times, or you can say roughly 7 out of 10 times, which may be still okay. But a recall to begin with a 51% is not good because it's as close to a random guess. You toss a coin, you can say head or tail. That's a 50% chance, right? So this is not doing that good for the ones. However, for early stage, the numbers still look better. For early stage identification, out of 100 cases, we were able to identify 89 properly. And whenever we said it's an early stage case, we were right roughly about 77 out of 100 times, or you can say 8 out of 10 times approximately if you round it up. And the performance as far as the test is concerned, it's more or less similar. We can see it as very comparable. So slightly better output in certain cases. For example, recall for the class 0 is 93 here, and precision is nearly comparable. And same goes for the precision for class 1. It's 79 here versus a 71. But the recall for class 1, which is the primary metric that we have, is only 52%. Why are we focusing on recall? Please understand, when we talk about healthcare, a false positive means that you might have flagged somebody as a person at last stage when the person actually was not. which is bad, but it simply means that the person will get subsequent checks done. And there's a chance that in future we'll not repeat the same mistake. We'll be able to say that the person is at an early stage. But a false negative here is very dangerous because it means that the person is at the last stage. We don't take it that seriously. And that's when the person is losing time. When false negatives are more important, it's the recall that becomes the metric of choice, because the formula for recall is true positive divided by true positive plus false negative. As of now, the results don't look that great. One fundamental thing that we need to understand here about the models is that how do they convert the probabilities that they predict into a class? Because naive Bayes is based on the Bayes theorem. So it must be predicting some probabilities at the back end, and it's translating those probabilities into classes. How is it being done? So it's done by comparing the predicted probability with a threshold of 0.5. Now, there's a lot of debate that can happen on why 0.5 is the right threshold, because 0.5 is equivalent to tossing a coin. Now, let's try to figure out how do we find the right threshold for a given model. That will be found from the trained data and will be applied to the test data. So what we'll have to first do is we'll have to take the model, the same model that we instantiated earlier, which is a Gaussian Naive Bayes model. And instead of using .predict, which predicts the classes, we'll have to use a method called predict_prob, which predicts the probabilities. We'll have to first go to the probabilities. The input here would again be xtrain encoded. And this output, if we don't really put this square bracket 1 thing here, it would give us 2 columns, which will be the probabilities of zeros and probabilities of ones. We are interested in the probabilities of ones, so that's what we obtained from here. Now, once we have these probabilities available, these will be given as an input to this function called ROC curve. We are getting this from scikit-learn metrics, which takes the actual labels and the predicted probabilities. It returns the false positive rate, true positive rate, and the threshold. And we can, of course, calculate the area under the curve using the AUC function, which takes the input as FPR and TPR once we get it from here. Now, what is the optimal threshold? An optimal threshold would be the one where the true positive rate and false positive rate are at the highest separation. The difference between them is maximum. True positive rate is something which is higher the better. We want it to be better. And false positive rate is something which is an error. We want it to be lower. So we are saying we'll settle for that specific threshold, which maximizes the difference between the true positive rate and false positive rate. All these concepts with proper visualizations have been explained in our video on ROC curve. So you may refer to it for more detailed knowledge of the theory. Here we are focusing on the application. Now, once you find the index, you may want to filter the thresholds for the optimal right threshold. Now, all of this work is happening on the trained data. And if we want to generate predictions, so this is a correction here, I may want to change it to train because we are right now referring to the trained data only. If we want to generate the predictions for the trained data based on that optimal threshold, what would be the new classification? That will be generated using this comparison. If a given probability is greater than or equal to the optimal threshold, if it returns a true, then that will be converted to an integer. So when a true is converted to an integer, that becomes a 1. If it's false and that's converted to an integer, that will become a 0. But we want to get this more for the test data, right? So what we are doing is we are visualizing the same output here using the matplotlib library. We are taking the FPR and TPR outputs that we got here, and we are doing some customizations with respect to colors and labels, etc., and generating a receiver operator characteristic curve, ROC curve as we call it. But how does our classification report change finally, right? So let's focus on that, right? So we will be now doing our predictions on the test data, encoded, and we will be predicting the probabilities for the test data. Finally, the predicted probabilities of test data will be compared with the optimal threshold. What is the optimal threshold? That we found from the trained data. Once again, the same logic. If the predicted probabilities are greater than the optimal threshold, as we learned from the trained data, it will return a true, and that will be converted into a 1. If not, that will be returning a false, and that will be converted into a 0. And finally, we are generating a classification report, taking the actual test labels as they were given versus the predicted test labels after comparing with this threshold. And then we are printing the optimal threshold value. We are also printing the classification report based on the optimal threshold for the test data. Let's see what happens. So we get an output, which is the ROC curve here. This blue dashed line here essentially is a line which talks about a random classifier. We seem to be doing better than a random classifier, and this also indicates this point as a threshold, right? So what we can expect a true positive rate now of around 80% with a false positive rate about 21-22%. Let's check what the classification report has to say. So this looks a little better. At least the recall, which was 51% earlier, has gone to approximately 80% or 79% to be precise. So it simply means that out of 100 cases that we got, we were able to correctly identify stage 4 in 80 of them, or 8 out of 10. And if we talk about precision, whenever we said somebody is at stage 4, we were right 60 out of 100 times. Like I said, in our case, recall is the primary metric because we don't want to miss out an opportunity to cure somebody. If we are extra careful, if we are more sensitive and we push some cases as false positive, that still is okay, though we don't want to promote it, but that still is okay because that is an opportunity for future treatment. So this was a simple application of a Gaussian Naive Bayes model, where we also learned how to find the optimal threshold. Hope you had something new to learn from this video. Thank you.